In our last video, we talked about what chemical equilibrium is, and now we're going to talk about a few concepts related to equilibrium constants. So this video is going to cover a bunch of different topics related to equilibrium constants, and so this is a basic overview of what we're going to cover, the four basic concepts, and we're going to go ahead and start with mass action expressions and the two ways that we apply the mass action expression when we're talking about forward and reverse reactions and what's going on. So the mass action expression is basically a formula that tells us what's going on in a reaction. And basically for our generic reaction with two reactants and two products, each with their own coefficients, the mass action expression is going to look like this. So each chemical species in the reaction, be that products or reactants, is going to have its concentration raised to a power which is equal to the coefficient in the balanced chemical equation. And each of these terms are put into a fraction where the products go on top and the reactants go on bottom. For example, here is a balanced chemical reaction where we have two ethenes plus oxygen making two acetaldehydes. And to write the mass action expression, remember the products go on top. So let's start with our products. We have acetaldehyde as our only product. So we're going to put that concentration raised to the second power because that has a coefficient of 2 in the balanced equation. And then on the bottom, we're going to put the concentrations of our reactants. And remember, we have two reactants, so we should have two terms down there. We should have the ethene term, which is raised to the second power because we have two of those in the balanced equation. And then we have oxygen raised to the first power, which means I could just leave off the coefficient. So that is the mass action expression. Now, at any given point in the reaction, the numerical value of your mass action expression is going to be equal to what we call the reaction quotient. We represent the value of the reaction quotient with Q. Here I have a subscript C, QC, which tells us that we're using concentrations to calculate our reaction quotient. We don't always use concentrations, and we'll talk about that at the end of this video. So going back to this reaction that we were looking at earlier, we're asked to calculate the value of Q for this given set of concentrations. So I've taken the mass action expression that we came up with earlier and I popped it down at the bottom of the screen here. And so what we're going to do is we're just going to plug the numbers that were given into that expression. So on top we have the concentration of acetaldehyde, so that's 0.1 molar, that's going to be 0.1 molar squared. Then on the bottom we have our ethene concentration, we're going to square that, times the oxygen concentration of 0.2. And so we can calculate then, the answer is 0.56. Now, what would happen if we had different concentrations? Well, it's really easy to throw up an example of a situation with different concentrations. So let's just plug those in. Again, we're going to plug in the number for acetaldehyde, 0.5 squared on top, and then the concentrations of the other two, which are both 0.1. So one of those will be 0.1 squared, the other one will just be 0.1. Those are going to go in the denominator. So we plug that into the calculator then, and we get 250. So if you look at these two numbers, you can see that as the concentrations change, the reaction quotient changes. So that will tell us something about where we are in the reaction based on the value that we have for Q. And we're going to talk more about what those Q values tell us later in this video. So our reaction quotient changes as the concentrations change. But what happens when we get to equilibrium? Well, at equilibrium, we said before, equilibrium is where the concentrations stop changing. And if the concentrations stop changing, that means that at equilibrium, your value for the mass action expression at equilibrium will always be the same value. And that constant we call the equilibrium constant. The equilibrium constant is the numerical value of the mass action expression at equilibrium. And so a lot of people are like, hey, what's the difference between Q and K? Well, you calculate them the exact same way, but K says this value is what we will find at equilibrium. Q says this is the value right now. And here's the thing. For a particular chemical reaction, your equilibrium constant will always be the same under similar conditions. So the equilibrium constant is really constant, and the reaction quotient is something that is changeable. That's why we distinguish between those two. Knowing that, we can calculate the equilibrium constant by just measuring the concentrations of everything in a system, both reactants and products, at equilibrium, and then plugging them into the mass action expression. So in this particular case, we have the reaction between ethyl acetate and hydroxide, and those two can react to form acetate and ethanol. The problem gives concentrations. Let's first come up with an expression for what we need to put in for the equilibrium constant. So this is our mass action expression. So remember, it's product concentrations divided by reactant concentrations. There are no coefficients of anything other than 1 here, so there's nothing raised to any power. Now let's go ahead and plug those concentrations in, and we get a value of 436. So just a quick review before we go on to the next section. We have this thing that we call the mass action expression. We know how to write a formula for it and calculate it, but we use it in two different ways. One is for the reaction quotient Q, which can be the value of this mass action expression at any time in the reaction. The second is K, which tells us that value at equilibrium. The next thing we're going to cover is a special rule for creating your mass action expressions. So I gave you the generic, here's how you put this together thing, but we have this rule that we don't put a concentration in there if it doesn't change. Okay, so if we have something that stays constant, why bother tracking it, right? We really care about what's changing, and so we're only going to put in concentrations that change. So in general, the things that don't change are pure solids or pure liquids. Now, why is it that their concentration doesn't change? It's because of density. So if you have, let's say, pure water, that has a density of 1 gram per milliliter. If you have a reaction that's taking place in that water that's making more water, is the density of your water going to change and suddenly become 1.03 or 1.05 or 1.07 grams per milliliter? It won't. Instead, what's going to happen as you create more water is the amount of volume is going to change. You can't change the density of water just by making more of it. And that's also true of solids, where they have a given density and you can't compress them and you can't expand them very easily without putting air in. So pure solids, pure liquids, we're just going to completely leave out a mass action expression. So for example, in this balanced reaction, we see solid calcium carbonate forming solid calcium oxide plus CO2 gas. This is what happens when you heat limestone. It produces CO2 gas and leaves behind calcium oxide. So if we write our mass action expression in the traditional way, let's say we're trying to find the reaction quotient, what we'll get is this. Remember, products on top, reactants down below. But we have to go through and take out anything that is a pure solid or a pure liquid. We don't have any liquids here, but we have 2 solids, so we can just chop those out. And so our actual reaction quotient will just be the CO2 concentration. And of course, this also works for liquids, like in this case, liquid mercury. And so we can again write a reaction quotient, go through, see what doesn't belong there, the liquid mercury can go, and so this is what our reaction quotient looks like. So that's our special rule. You will actually see that used a lot in chemistry, and mostly it's because of the formation of water. A lot of reactions use or produce water, and just remember you have to leave the water out. Okay, now we're going to dive into why we need both the reaction quotient and the equilibrium constant to tell us what's happening. So going back to the reaction quotient, let's think about what happens under certain conditions. What happens if you have a lot of products and fewer reactants? What's going to happen? Remember, all of your product concentrations go on top. So you have big numbers on the top of this fraction, you have tiny numbers on the bottom. So if you have a big number divided by a tiny number, you end up overall with a very large value. What happens if you have more reactants than products? Well, then you're going to have big numbers on the bottom of your fraction, and you're going to have tiny numbers up above in the numerator, and so you're going to have a tiny number divided by a big number, and you're going to get a really small number. So looking at how large your reaction quotient is tells you whether you have more products or more reactants, and the bigger the number, the more products you have, and the smaller the number, the fewer products you have. Now let's talk about equilibrium constants. Well, basically, we're using the same expression to figure out a reaction quotient versus equilibrium. So if Q is large, that tells us there's more products than reactants. If K is large, that tells us that at equilibrium, there are more products than reactants. In other words, when the concentrations stop changing, you will have ended up with more products than reactants. Now let's talk about the opposite case, when Q is small. Q is small tells us that we have more reactants than products at any given time. If K is small, that tells us that at equilibrium, when the concentrations are no longer changing, you have a lot of reactants and almost no products. K is large when we have more products than reactants at equilibrium. K is small when there are more reactants than products at equilibrium. So remember, in our intro video, I showed you this reaction between hydrogen gas and oxygen gas, and I said, is there really a reverse reaction if we sit there and we look at a water bottle and we never see hydrogen gas or oxygen gas bubbling out of it? Is there a reverse reaction? Well, let's look at our equilibrium constant, and it is enormous, 9.1 times 10 to the 80th, which means there are far more products than reactants at equilibrium. Okay, so next we're going to talk about predicting what's going to happen with a system. And basically, let's just say you throw together a bunch of chemicals, some of which are the reactants of a forward reaction that could produce products, and some of which are the products of that forward reaction, which are then the reactants of the reverse reaction. Okay, so these things can go either way. And the question is, will you make more products or will you make more reactants? And we can figure out which will happen based on our reaction quotient Q. So what we're going to do is we are going to compare our reaction quotient to the equilibrium constant. If our reaction quotient is greater than the equilibrium constant, what does that mean? That means we have more up on top of the fraction than we should have. And so what we're going to do is we need to make those numbers on top smaller to lower our overall Q value, because we want to get to equilibrium. There are more products than there would be at equilibrium, so the system will get rid of the excess products by creating reactants. Now let's look at the other case. If the reaction quotient is less than the equilibrium constant. If the reaction quotient is smaller than the equilibrium constant, that's because you have larger numbers down below than you want to be at equilibrium. And so that means you have what's down below. And what's down below in your mass action expression? It's the reactants. So there are more reactants than you need for equilibrium. The system has to get rid of those excess reactants, and it's going to do that by turning the reactants into products. So basically, you're going to look at your value for the reaction quotient, see if it's larger than or smaller than the equilibrium constant. If it's larger, then your products are going to turn into reactants. If it's smaller, your reactants are going to turn into products. And then one more possibility is, what if your reaction quotient is equal to the equilibrium constant? Then you're at equilibrium and the concentrations aren't going to change at all. Okay, one more thing we're going to talk about is we're going to talk about Q sub P and K sub P. So if we're looking at equilibrium in gases, we could do it the way we've done everything else, but the problem is we almost never measure concentrations of gases. We almost never tell how much gas there is in terms of molarity. What we usually do is we measure gases by giving their partial pressure. So we can write a different sort of equilibrium constant. This is the sort of equilibrium constant that we were talking about before, where we put in the concentrations and raise them to the powers. But we could also write one for pressures, where we have the pressures raised to the power of the coefficients in the balanced equation. And we differentiate between these two by the subscripts. So the one with concentrations is K sub C. The one with pressures is K sub P. And by the way, that's also true for the reaction quotient, Q sub C and Q sub P. So K sub C and K sub P will not necessarily be the same numbers. So what is the relationship between them? To understand that, we have to go back to the ideal gas law. PV equals nRT. Now, if we divide both sides by V, we get pressure equals N over V times RT. And what is N over V? Well, that's moles divided by volume, which is molarity. So the pressure is going to be the molarity times RT. And so here's this factor of RT that's going to keep coming up over and over again. Let's look at how K sub P is related to K sub C for any given reaction. And to do this, we'll look at our model reaction that we've been using this time. So K sub P is going to be the pressure of acetaldehyde squared divided by the pressure of ethene squared times pressure of oxygen. Okay, so what we're going to do is take our revised ideal gas expression, and everywhere that we see a pressure, we're going to plug in molarity times RT. Now I've done that. Okay, and then what I'm going to do is I'm going to rearrange the terms in this fraction. Basically, I'm going to take all the concentrations and stick them on one side, and then I'm going to take all the terms with RT in them and stick them together. And I've color-coded which ones are the concentrations versus the RT. And if you look at this expression for Kp, what you'll see is part of it, the part with all the concentrations, is actually equal to Kc. And then the rest of it is a factor of RT, right? Because a bunch of those RTs will cancel out with each other. So we end up with 1 over RT. So we can now make a generic equation that relates Kp and Kc, where Kp is going to be Kc times RT raised to a power that we call delta N. What is delta N? It's the change in the number of moles of gas during a reaction. Now, if you go back to our actual reaction and you look at this, you see that we started with 3 total moles of gas, 2 of ethene, 1 of oxygen, and we ended with 2 moles of gas, acetaldehyde. So our number of moles of gas dropped by 1. So delta N is minus 1. And so we had in that final thing 1 over RT, which is RT to the minus 1. So now we can use this in a problem. Water plus methane gives us carbon monoxide plus 3 hydrogen gas. And we're given a value for Kp, and we're asked what the value for Kc is at this particular temperature. So here's our formula for the relationship between Kp and Kc. Right now we have solved for Kp. Let's rearrange it so Kc is on one side and everything else is on the other. The next thing we need to know is what is our delta N. And so if you look at this, we have 2 moles of reactants. We have 4 moles of products. So delta N is 4 minus 2, because it's always products minus reactants. That gives us 2. So let's plug this into what we've got. Kc is going to be our value for Kp, 6.1 times 10 to the fourth, divided by RT, where R, again, the perpetual question of which R do we use? Well, remember, we're talking about pressures. We're going to use the one with pressure units. Okay, so 0.0821 liters atmospheres per mole Kelvin times 1125 K, which is the temperature we're given in the problem. And that whole thing is going to be squared because our delta N is 2. So when we run that through, we see our Kc is 7.2. So equilibrium constants help us understand if we're going to have more products or more reactants when we hit equilibrium. We can look at concentrations, calculate the current reaction quotient, and understand whether we need to create more products or create more reactants. Equilibrium constants are very useful in helping us understand a system. I hope this was helpful, and I will see you again soon.